mean by functions of multiple variables? Function of more than one variable means, so let's start with functions of two variables. Okay, while a one-to-one function, let's say, which is y is equal to fx, function of one variable, not one-to-one, function of one variable, y equal to fx. In this case, x is the variable. Okay, so it is a mapping of it is a mapping of so f is a mapping of values of x, values of x to values of y. It is a mapping of values of x to values of y. However, consider a function of two variables. Let's say z is equal to f of xy. In this case, it is a mapping of ordered pair of variables x and y. X and y are the two variables, and f is the mapping of values value of values of ordered pairs ordered pairs x and y, x comma y, ordered pairs of variables x y to the values of another variable, which is z. Okay, so for example, so f of x y, now this has two variables. So let's say all of you know the equation of a circle, right? So let's say z is equal to f of xy, which is equal to x square plus y square, is equal to x square plus y square. Okay, so in this case, x square plus y square is the domain. So here the geometrical interpretation is, in this case, because it's a perfect circle, so here will be a circle. Okay, the domain is a circle. We take any ordered pair x y from this domain, and this is mapped to a range, which is values of z. So this particular x y, okay, it will be mapped to some particular value of z. This is the definition or the meaning of a multi-valued multivariable. This is the meaning of a multivariable function of more than one variables. Okay, so let's take some another example, simpler example of a multivariable or function of two variables. Let's say f of xy is equal to 2x square y cube. This is also an example of function of two variables x and y, and there is an implicit z equal to over here. Okay, but 2x square y cube is a function of two variables x and y. Okay. The next thing is partial derivatives. So why do we require partial derivatives basically? Okay. Consider the case that we have a function of one variable fx. Okay. In case of function of one variable, the of the function derivative of the function y will be dy by dx. Okay, the notation is f dash of x is equal to dy by dx. Here we are measuring the rate of change of the value of the function, that is it is actually d of fx upon dx. So here we are measuring the rate of change of the function fx as x changes. Okay, now what will happen in case of multiple variables? When a function is when we have a function of more than one variables, what do we do if we only want one of the variables to change at a time? Okay, or if we want both of them to change but in different ways. Okay, so the change in x, let's say z is equal to f of xy, and the change in x is not the same as change in y, or we only want to measure the rate of change of f when only one of them changes, like for example when only x changes or when only y changes. Okay, so for that we require partial derivatives. Okay, so let's say we want to find the rate of change of this function f of xy is 2x square y cube. We want to find its rate of change at a particular point, let's say at a point a comma b, where a and b are some constants. A and b are constants. This is a point. This is a point actually, point where we want to measure the rate of change of f. Okay, so now we want to find the rate of change of f, and we'll see two cases now. Let's say we want to measure the rate of change of f at the point AB when y is fixed, and when y is fixed when y is fixed and x varies. X varies. Okay, so y is fixed and we are at the point AB. Okay, this is case number one. Let's say y is fixed, x varies, we are at the point AB, therefore y will always remain B. If you have any question, any doubts at any point, you can interrupt and ask. Okay, so when y is fixed, y is equal to B. Okay, so effectively our function becomes, so f of xy becomes a function only of x. Let's call that function as g. So g of x is equal to 2x square b cube, because y is equal to b. So this now becomes a function in only one variable, that is x. Okay. Now we want to compute the derivative. Rate of change of any function means the derivative of that function. So we want to find the rate of change of g of x at the point x is equal to a. Okay. Find g dash of x at x is equal to a, or in other words, find g dash of a. Let's see. Where a is a constant. A is not a variable. A is a constant. Okay, is some constant at some point. Now the derivative of this function is, now you will have to revise the, for this model you have to revise the rules of derivatives and the basic formula of derivatives. I will share a sheet with you uh, regarding the basic formula of derivatives and the rules. So 2x square, the derivative is 4x. 2 remains as it is. Derivative of x square is 2x. So 4x b cube. And when we say that we want to find, so this is g dash of x in general, and g dash of a will be 4ab cube. Okay, so assume that these are some values. Let's say the point is 3 comma 4. These are some constants. Okay, so you will get some value, basically some scalar, some value you will get for this derivative. Okay, this was case 1, when y is fixed, x varies. Now let's consider the other case, which is when, okay, so the main point is, this is called as the partial derivative of the function, called as the partial derivative of the function f with respect to x at the point ab. Okay, and one of the notations for it is f subscript x, and there are some other notations which we'll see later, but let's say this notation is f subscript x, which denotes derivative, partial derivative with respect to x at the point ab is equal to 4ab cube. Now consider the case when x is fixed and y varies. Okay, so when x is fixed and y varies. Okay, so, and again we are finding it at the point ab. So because x is fixed and we are at the point ab, so x is equal to a. So our function now becomes a function of y, which is 2a square y cube. 2a square y cube. Now again calculating the derivative of this function, d of hy upon dy is equal to 2a square is a constant, remains as it is, y cube, the derivative of y cube is 3y square, so it becomes 6a square y square. This is h dash of y. And now when we say we want to find h dash at the point y equal to b, okay, we want to find this at the point y equal to b. So this is h dash of b is 6a square b square. So this is nothing but partial derivative of f with respect to y at the point ab, which is 6 6a square b square. Okay. So any questions up to this point? Any doubts? Any questions up to this point? You can ask. No doubts? No. Okay then. So let's continue. So let's take another function and you find the partial derivatives of it. Let's take a simple case. F of xy is equal to 3x plus 5y plus 2. What will be the partial derivative with respect to x? And okay, so let's say you are not given any point. Okay, just find it in general. Partial derivative of the function at x. Okay, so let me also introduce the additional notation over here. So the additional notation is, okay, one of the notation is fx, and you are given the point. Okay, any point you are given, let's say at the point xy, where xy are some values basically. You are given a point at which you will calculate it. You are not given the point, it will just be f of, okay, these are the notations for partial derivative with respect to x. Okay, so fx, it will include x in the expression. It will include the variable x in the expression, and then uh, another notation is this d with a slight curve on the top, actually, with a curve on the top. D with a curve on the top. It is called dou f upon dou x, or daba f daba f upon daba x. Dou f or daba, dou or daba. There are two ways you can call it. Okay, or you can also write it as d, capital D with subscript x, of f, as if you are operating this operator d of x on the uh, on the function f. This is like an operator dx which you are operating on the function f. Or last notation is, let's say z is equal to f of xy, then one notation is also zx, but this is not recommended as a notation. I would suggest you follow either of these three notations. Fx, this is too much of a writing, dou f upon dou x, but this is standard actually. Dou f upon dou x, dou f by dou x, or you can write dx f, up to you. So I'll just write fx right now. Okay, so, or okay, I'll use another notation for a change. Let's say I'll use dou f by dou x. So find dou f by dou x for this function, and dou f by dou y for this function. Okay, dx is 3 and dy is 5. Simple. Now, slightly more complicated one. Let's say is equal to, now you need not open this square term. Don't open this term. You can calculate it as it is using the chain rule. Reply yes in the chat. If you know about the chain rule, then reply yes, or I'll show how. You know the chain rule, right? Okay. So in this case, first we'll consider the entire thing as a some variable, something raised to square. It will be solved first. Okay. So okay, let's say I'm considering x as a variable, x square. So something square, not x actually. Entire bracket, consider we are considering a square of something. So it will be uh, 2 times x plus 2y, the entire thing basically. Okay, consider this entire thing as another variable, let's say m or whatever a variable square, and you are taking its derivative. This, then followed by, then go inside, you will see this, then find the partial derivative of this, which is 1 because the coefficient of x is 1. Therefore is equal to 2 times x plus 2y cube. Similarly, when finding partial derivative with respect to y, in this case, so if I do y will be 2 times x plus 2y cube, dou by dou y of x plus 2y cube. Now derivative of y will be y cube will be 3y square multiplied by 2 6y square, and okay, so really I'll just not omit this step, 2y cube multiplied by 6y square. Taking the constants together, you can write 12 x plus 2y cube multiplied by pi square. Did you understand this? Any questions, any doubts? You can interrupt, ask, and continue. Okay. Next is trigonometric functions. If you remember the derivatives of z is equal to f of xy is equal to x cos y plus y. Reply with the derivatives. Both. Okay, please repeat which part, Akash. Okay, chain rule means, okay, basically it's like composite of two functions which is applied. Okay, so firstly you are applying this function, that is x plus 2y cube. This is one function which you are applying to xy. and then another function that you're applying is you're squaring it. Okay, so first you will solve the outer function. The outer function is y square. Just like, okay, let me call it some, okay, let's say this is entire thing is m, let's say m square. So as per the chain rule, what you will do first is you will first differentiate this one. So it's like you're finding df by dm first. So df by dm, which is 2m, and then you are applying to the inner function, you are applying uh, d by dx. In this case, dou by dou x, because it is partial derivative with respect to x. So you are applying dou by dou x to the inner function. Okay. Similarly, in case of y, you are first. Similarly, in case of y, first you'll have to solve this m square, which is 2m. This is m, 2m, and then find the partial derivative of the m itself. That is this. So effectively it is effectively like finding df by dm, and then finding dou f by dou x and dou f by dou y respectively. Okay, got it? Yes. Okay, next question is dx is equal to cos y. Yes, cos y, and dy is not 1. Dy will be x will be a constant, x sin y, no, yes, minus x sin y plus 1. Yes, correct. Minus x sin y plus 1. 2 y2. Acha, you are okay. You are okay. Fine, fine, fine. Okay, okay. Yes, 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 yes. Got it, got it. Okay. So you have got this concept. Let's move on to the next concept. That is, so I'll share the table of derivatives, and so you'll solve some more examples in tutorial. So let's move on to the next concept here. That is the concept of a gradient. Okay. So what is meant by a gradient? Okay. A gradient.
Hello, sir.
Yes.
Can you explain the last part?
The derivatives of this function, fx.
No, x cos y plus y.
Answers for this you're saying.
Yes.
Okay. Okay. So dx is basically y is considered a constant here. So uh, cos y, and dy, because y is a variable, so x is a constant. So it's so derivative of y is 1, and derivative of x is a constant. This is the answer. Okay. Is what Aditya, right?
Yes, sir. Okay.
Okay, fine. So let's move on to the next concept, that is gradient. Okay, so basically gradient is an operator which, when applied to a multi-valued function, or any function actually, it can be single valued as well, it converts that function into a vector. Okay, so Okay, and also, okay, one more point that was left. Uh, Here I'm stopping at variables of, sorry, functions of two variables. This can be applied to functions of more than two variables as well. Any number of variables you can have. Okay, so here I'm just stopping at functions of two variables. If required, we may also see functions of three variables later on. Okay, but the thing is the same. There you can additionally have dou f upon dou x, dou z. Let's say if you have functions of three variables. Okay, then the function will look like w is equal to f of x y z. Okay, function of three variables, and we won't require for this course at least functions of more than three variables. Okay, so coming back to gradient is an operator. It is written as this del operator, downwards triangle f x y. This is the function to which this operator del is operated on. This is equal to dou f by dou x I cap plus dou f by dou y I cap dou f by dou y j cap, where I cap is the unit vector in the x direction and j cap is the unit vector in the y direction. Okay, so the function initially was a scalar. Function was a scalar in the sense z is equal to f of xy is a scalar. Do you agree with this point? If you any one of you has a doubt in this point, you can ask here. Z is equal to f of xy is a scalar function because f of xy, when you substitute the values of x and y in this, ultimately you get a number. As we saw in the diagram earlier, I'm not scrolling up now, but as we saw in the diagram, the domain is two dimensional. Okay, but the range it's still a one dimensional number basically, that is z. Similarly, w is equal to f of xyz also, if we consider, it is also a scalar function because when you substitute the values of the variables in the function f, you get a scalar. Okay, so when the gradient is applied to a scalar function, it gives you a vector in this way. Okay, so for example, let's say, let's take these examples itself. Okay, so the first function that we saw was f of xy is equal to uh, 2x square y cube. Gradient of f of xy will be dou f by dou x. Now here we are not considering it at any particular point in general. So dou f by dou x will be, y is a constant. So 4xy cube I cap plus, you can also omit this caps because if there is no scope for any confusion or any ambiguity, any, so you can omit this cap. If there are any variables named I as well and there can be confusion, then you have the cap. Otherwise, you can omit it. So plus uh, dou f by dou y, in this case 2x square becomes 6x square y square j cap. Okay, similarly the second one that we saw, I should have numbered them actually, then it would have been better. 3x plus 5y plus 2. I'll write it here itself, okay, because all of them are named f coincidentally. So gradient of f of xy in this case is is 3 I cap plus 5 j cap. In this case, in this case, in this case, you get the point, I think, right? You get the point. Dou f by dou x I cap. So the gradient will include adding, this component I cap and this component j cap. Okay. Similarly, in this case, you will have dx I cap and dy j cap. That will be the gradient of f of xy in this case. Okay. So this is the gradient. Now, what is the interpretation of this? Okay. So the component, basically, component of the gradient in any particular direction. This is in 2 dimensions. Let's say we can also define it in 3 dimensions. Okay. So gradient of a function in 3 dimensions, you'll have dou f by dou x I cap plus dou f by dou y j cap plus dou f by dou z k cap. Okay, in general. Okay, so you can have unit vectors in any number of directions. 3 is sufficient for now. So any particular component, let's say dou f by dou x, this component denotes the rate of change of f in the direction of that particular variable, that is x. Dou f by dou y indicates rate of change of f in the direction of y, and dou f by dou z indicates rate of change of f in the direction of z. Okay, so as a simple case, so this is okay. So, and again at that particular point, so let's say you can substitute the values of x and y in this case, and then find out what is the rate of change of x. This is the rate of 4x y cube is the rate of change of x at the point xy. So if I substitute 3, 4 here, at the point 3, 4, the rate of change of x is 4 raised to 4 is 256. 256 multiplied by 3, 768. Okay, so rate of change of x is 768, and similarly you can calculate rate of change of y. You get the point? So this is the physical interpretation of the gradient. Okay, or it can be, so this is like a linear function. Okay, 3x plus 5y plus 2, this is a linear function in the variables x and y. It is linear in both. So rate of change is simple, 3i plus 5j. It's a constant rate of change. Because it's linear, the rate of change remains constant throughout. X increases by 3 and y increases by 5 at every step, basically. So, sorry. What I mean to say is, fx, z, that is z is equal to f of x, y. So z increases by 3 steps at every step of x, and z increases by 5 steps at every step in the direction of y, basically. Okay, so this is the physical interpretation of the gradient. Okay, so that was for partial derivatives and gradients. Now let's move on to what if the function itself, the multi. So okay, so in data science we have the terms univariate, univariate, and multivariate functions. Okay, so if a particular quantity, that is an attribute or a variable, is a dependent variable and it depends only on another variable, then we call it as univariate dependency. Or if we have a dependency like this where z depends on the variables, more than one variables x and y, then we call it as a multivariate dependency. Or we have a variable w which depends on the variables x, y, and z. We also call it as multivariate dependency. Because okay, so ultimately these are, we are leading to machine learning and machine learning concepts only. So I just introduced these terms. Okay, so what if the function itself is not a scalar function? Okay, what do you mean by a function that is not a scalar but actually a vector? So for example, so this is the definition of a function, and these are called as vector valued functions. Vector valued functions. So these are the functions in which when you substitute the values of the variables, you get a vector as the result and uh, not a scalar. Okay. So a vector valued function is, normally it is denoted by r. So r vector, and it is, so we are considering single variable vector valued functions. Okay, single variable vector valued functions. So the common example, you must have studied physics at some point. Let's say, so r vector is normally used for displacement. So r vector as a function of time. So even though this is, so generally this is the notation. So this is our function. This is our vector valued function r. The single variable that it depends on is t, and it is given by, or it is defined as uh, f of t I cap plus g of t j cap plus h of, so it is only, let's say it is two-dimensional case, but you can also have, let's say, three-dimensional case where you can have h of t k cap. Okay, so the component functions f, g, and t, f, g, and h, sorry, f, g, and h are are still scalar functions. Are still scalar functions. Okay, so for example, you can have, uh, think of anything like, let's say r vector of t is any, t square plus 2i plus 3t plus 1j. Let's say, let's restrict ourselves to two dimensions only, let's say. Okay, so when I substitute t equal to 0, it will be 2 I cap plus j cap. We don't write one j cap, just j cap. 2 I cap plus j cap. Substitute any other value, let's say 2. When t equal to 2, it will be 4 plus 2, 6 I cap plus 6 plus 1, 7 j cap. Okay, so this is a vector valued function. It returns a vector when you substitute the values of the variables in it. Okay, and you can also plot these functions. You have plotted vectors in the previous term, so you know basically if I say if I say like, so such questions won't be there, but let's say if you want to plot this, then it will be 2 units along x, 1 unit along y, and okay, so 1 unit along y, 2 units along x, and it will be something like this basically. Okay, similarly at this r2 it gives. Okay, now, so any questions in this vector valued functions? Voice is low. Is it better now?
Yes, sir.
Okay. Okay. So yeah. So if there is no question in vector valued functions, let's move on to now finding the derivatives of a vector valued function. Okay. Still restricting ourselves to single variable vector valued functions. Okay. So r vector is the function, and we want to find the derivative of r vector with respect to t. Now, by the basic definition of a derivative, it will be limit delta t tends to 0 r of t plus delta t minus r of t divided by delta t. Okay. Now, if we actually want to evaluate this, it actually what we are doing is this operation applies to both of your components. So effectively, if r vector of t is f of t I cap plus g of t j cap, and you can also let's say uh, h of t k cap, then effectively the derivative of r with respect to t is the derivative of f, derivative of individual components basically, g dash of t k cap plus h dash of t k cap. Okay, so if you want to find the derivative of a vector valued function, you have to find the derivatives of its individual components. Okay, so let's say our function is, take a simple function, it is 3t plus 4 I cap plus t square minus 4t plus 3 j cap. So the derivative is nothing but, because there is only one variable, it is straightforward. It is just 3I cap plus 2t minus 4 j cap. Okay? Derivative. Okay? This is the concept. Okay, so let's again see some examples of this. Let's say one more example. RT is equal to 3 cos t I cap plus 4 sin t j cap. Okay, so the derivatives will be derivative of cos t is minus sin t minus 3 sin t I cap. Derivative of sin t is cos t, 4 cos t j cap. Okay, any questions in this case? Explain limit part. This is the basic definition of any derivative. Okay, so uh, let's say this is any function and you want to find the derivative. Let's say this is the axis of r and this is the axis of t. So you want to find the slope. Let's say you want to find a slope at any particular point, but you cannot. So what you will do is you will try to find one portion of this, okay, such that uh, for a very small displacement in t, infinitesimally small displacement in t. So here at this point, the value is t equal to t. This is t equal to, this is t equal to t, and this part is t equal to t plus delta t. So when t changes by an infinitesimal amount, that is delta t, how much does, so this is the change in t, this is the change in t. So when the t changes by this infinitesimal amount delta t, how much does r change? That will be the derivative of r with respect to t. So at this point the value is r of t. Here we have r of t and here we have r of t plus delta t. So we subtract it and we find. Okay. Okay. So now the next concept is gradient of a vector valued function. but that concept will also require multi-variable vector valued function, which we'll see in the next lecture. So today, until now, whatever the attendance was registered using the Google Meet attendance add-on. Additionally, what I am going to do from today is don't leave the meetings. Okay, if don't leave the meeting. I can see 42 students were here right now. So I'll just read the names surname wise, and you can answer me, and then you can leave the meeting. Okay, so I'll start in alphabetical order of surnames. Okay, so Bharat Agarwal.
Yes, sir.
Okay, Abhijit,
Yes, sir. Present, sir.
Zainab,
Yes, sir.
Mohid, Mohid is not here.
Yes, sir.
Yes, okay. Hemant, yes.
Yes, sir. Present, sir.
Suyog, okay. Akash,
Yes, sir. Present.
okay. Aaron,
Yes, sir. Present.
Ananya,
Yes, sir.
Aniket,
Present, sir.
Aman, okay. Kanath,
Yes, sir.
Gitesh,
Yes, sir.
Chintamani,
Yes, sir.
Safat,
Yes, sir.
Sai Kiran,
Present, sir.
Sunil,